Hello, my name is Andrew Colvin and I'm going to show you the Service Analysis Performance tool and how it operates. To start, we'll start the program. It's a fairly simple start. There's a little script that just runs. This is running on a Unix server, but you can actually run it on Windows as well. It can be run just by double clicking the jar file. It's a Java based program and runs fairly easily and quickly. It's got a few windows here. I'm just going to close them. We'll come back to them, and there's some extra ones. So this is the main window. This opens up and it's got a few columns. It's based on a table, so you get the first column here, which is a type, because we'll see. You get a service operation component, function, whatever you want to call it, number of samples, the rate the samples came in, number of consumers, number of dependents it has, the mean, some other things we'll come across in a little bit, standard deviation, the median, assuming it's based on a log normal distribution, the mode based on a log normal distribution, and effectively the wait time that service had in it for other things to complete. So let's start by actually loading up a model. So we can load everything that through the load file. It can load different types of files, so I'll just go and find a model. I've got a test one. It comes in the release pack, the test data and the test model, so you can try things yourself. So here's our model. Okay, the status bar tells me it's finished loading. So there's different types, so there's UI types, there's BW types, services if you like, there's database calls, there's work streams, they're like use cases. There's a bit of TK, which is I put in as think time, that we'll talk about later. So let's just pick one of these. So process 1 op 1. Okay, I'll open the service dependency model. So here we go, service dependency model. So here's process 1 op 1. It's drawn like a UML diagram. It's not true UML, but it draws itself like it. So that is actually called by the one consumer, as it says it has one consumer, portal screen 1. And that calls one dependent. It's got one dependent, process 2 op 1. Process 2 op 1 actually calls process 3 op 1, package 1 procedure 1, and package 1 procedure 2. Process 3 op 1 actually calls package 1 procedure 3 as well. So we can actually see the full dependency model of what calls what. Okay, this is useful for later on, as we'll see. So I'm just going to close that down. We can come back to that whenever we like. We can also click on these ones and it'll allow us to zoom in on them. We can go back and we can see package 1 actually is called by these two here. Okay, so you can also change them here, and that changes the graphs in that table. Okay, so we've just seen the dependency model. Now let's load some data. We've got some test data. It was in the same folder that came. Test data. And this is just a load of sample data I just created, and it will just load in. Okay, all the data is from a log normal distribution. As you can see, it's just loaded up several tens of thousands of samples rather quickly. It's gone through. It's telling us the rate. Those samples all have a time they occurred, so those are the rate they were being called effectively from the times. Here's this list here, tells me the mean, and as I said, there's the standard deviation, there's the log normal, there's the log mode. These samples don't have any, they're all sort of set wait time. I didn't actually do anything, so just not to worry about that. We'll see that come into play later on. So let's actually look at that process 1 op 1. Okay, I'm going to reopen up the service dependencies. There we go. Just refresh it by clicking on. If you look at process 1 op 1, we've now got 4 numbers. These numbers are the count, the mean, and these two here are the 95th percentile and the 98th percentile, assuming it's a log normal. Okay, and you see that, so you can actually see visually that calls that, and that's 125 milliseconds of that, which is 219. Okay, how does it get all these? Well, it actually requires your program, your COTS product, whatever it is, to actually output some statistics. You can output them in any format and write a little extension to load them, but you need to output them. So we've got standard extensions, or ones to read VW statistics files. We've got some to read our portal log files. We wrote some special lines in our portal. We can turn them on and off, which actually generates data. We can use Yahoo's Boomerang, and that actually creates a log entry from the actual client's browser, and we get real statistics from the browser then if we load those up. And it's very simple. We'll look at the extensions later. We've just loaded this data. So what does this sample look like? They can't all be at 219, so we can actually look at the service frequencies. That opens a graph. I've actually opened my other screen, so I'll just drag it across. So on this graph we've got the red graph here. That's actually all my samples. So the sample at the bottom is the sample responses along the x-axis, and up the side is the frequency, i.e. the number that was at, say, 1000 milliseconds, or the number at, in this case here, if I hover over 275.5 milliseconds. Everything is quantized into units of 1 millisecond. So 0.1, 0.2, 0.3, 0.4 are all fall into the 1 to 2 millisecond bracket, to 1 millisecond bracket, and therefore be shown as 0.5. The blue line is the cumulative frequency distribution, and it's measured on the scales, and it goes from 0% up to 100%. So by the time we reach here, we've had 100% of our samples. If we go along here, this is our median, which is somewhere around here. You can actually zoom in on these if you want to and get quite close. I'm just going to pull this down so you can get rid of the red, so I can see if my 50%, there it is, comes down, so it's approximately 150 milliseconds. Okay, so that's I'll just bring this back in, and we got a lot of, if you right click, you got a lot of entries, so we'll just zoom both things, and we'll quickly have a look. There's some properties in the graph, and we can go and change things, titles, show title, turn it off, change plots. So all of this is in there. All of these can be changed, so you can tweak your graph if you wish to. You can copy it, you can save it, you can save it as a PNG, you can print it directly to a printer, you can zoom in and out. Okay, we can turn off the frequency distribution, the cumulative frequency distribution, if we don't want it. There, and we can also turn off the frequency distribution by pushing my sample width to 0. Or we can go back to 1, or we can simplify the graph and have bigger quantization. So if I move it to 20, that means everything from 0 to 20 goes in one bucket, everything from above 20 to 40 goes in the next bucket. My graph looks much simpler. I can actually now see where my mode is. It estimates based on that quantization, which is actually 5.5 with 212 samples, and the graph looks much simpler. Well, we got on the right hand side, we got effectively two lists. In this case there is only one in each. So this is the consumers, and on the bottom is the dependents. So I can actually plot my consumer on here as well. So this light blue is the consumer's frequency distribution, so I compare process 1 against the portal screen 1. As you can see, it's wider and it's shallower. I can also put on process 2 up 1, and I can also take off, and we can plot different bits against different bits. So as you can see, we can actually compare the frequency distributions from one graph to another function, see if there's any comparison, any linkage, if something is driving, if one dependent is driving its consumer, and it's useful for actually tracking down if there may be problems, if there's where we should actually focus our efforts. So let me close this frequency distribution now. We've got another graph. We've got top service times. Now these are two graphs in here. So we'll just switch this to everything. But before we look at that, that one, we'll focus on the percentage graph. So what the percentage graph is, it takes the number of samples, multiplies it by the average, so it gets total time. It does this for every operation, and then says what percentage of the total they're using, and only shows those that are using more than 1%. In general, you'll find most things don't use more than 1%, and there's only a few left, and they're the ones we found we need to focus on most, because they're using most of the CPU time, either because they're being called so many times, or they take a long while and been called a moderate amount of times. If of course something takes a long time but it's only called once, it may not appear in this graph. You still may want to look at that because it's taking a long time, but it's not taking an overall. If it's called once a day, yes, maybe you'll leave it. That's what this graph will show us. This graph, we can actually zoom things in and we can zoom in and out. It starts at 300, so it only shows things above 300. So I've just pulled it down to 0, so it's showing everything. And this actually shows the amount of time this averages for each of these different things and lists them from worst to best. So you can immediately see which things are your worst. User think we set it manually of over 1 second limit, so I'm just going to pull this down so it disappears because I'm not interested in it. Okay, and therefore it shows us our worst. Our portal screen 1, portal screen 2 are worst. We might want to do some work on those to try and make them faster. Now they do call these things, of course, so they're built up with some of this, but there may be their own functionality in there. Maybe downloading lots of stuff. We have a box up here, and you can actually tell it to only look at either the UI or the BW or everything. So there are our top service times. When you close one of these windows, they all go. But again, it uses the same capability. You can zoom in, you can change properties as the previous graph. So we'll just close those. There's one other window in this list, and that's the volumetrics model. The volumetrics model is there to allow us to model the business. Okay, so we've got here two components. This one says widget A, so widget A here, and we got to fulfill 5,000 of those widget A in a unit of time for the business. Okay, widget A is made up of an order, a fulfill, a deliver, a bill, a collect, some think, and this is the quantity of those. Okay, these are our work streams up here, i.e. they are the use cases. These could also be classed as use cases, but treat these as use cases, treat these as business processes if you like, although a use case and a business process fairly similar. So here we've got the amount of time. This is calculated from, so if we look at this order, this is calculated from all the services it calls. So if I show you the service dependency, so workstream order calls portal screen 1, which calls process 1 op 1, which calls process 2 op 1, which calls everything else as we've already seen. So it walks that tree. So it walks the portal and says I've got to call this 5,000 times. There can be multipliers on these built in the model. So if it uses 3 of those portal screen 1s, it would have it 3 times. But in this case it's 1, because you can see. So this is how much time an order takes. Fairly simple model. A real one would be much complicated. And then it goes through and multiplies them all up and comes up with a number. What good is that, you say? Well, the reason we do that is because we may have a certain number of these we need to do in a day. We know how many milliseconds, whatever these times are, in a day. We've got the user's time, their think time, or their time actually doing something while they're waiting for the system or not waiting for the system. So we can add up and make sure it all fits in a day. We can also do some what ifs. So if I go back up here and I take package 1 procedure 2, I can't remember if this one was called, it's taking 77 milliseconds. Let's say I can do some work and take 20 milliseconds off of that. Okay, that actually says an adjustment 20 milliseconds, and that will bring my current execution time down to 57. In this example, it hasn't actually rippled up. So let's look at package 1, procedure 1. This is currently taking 19. Let's say I can take 8 milliseconds off of there. Okay, so that ripples up to here, and it also ripples up, and you can see that 8 gets trickled all the way. If I now click on calculate, that will tell me I've got a 0.4% saving to the business on the widget A and a 0.5% saving doing widget B. We can actually then add on another one. So if I take 10 milliseconds off of there, you can now start to see they compound, so I get better and better. My saving is a 2% saving to the business now, which isn't too bad. So if I now start going up and go, right, let's have a look at process 3 op 1. 151. What if I can take 50 milliseconds off of there? All of a sudden I'm up to 8 milliseconds. So with 3 small changes, I can actually save 8% of the business time on doing widget A. So we can do what ifs, we can make sure we can fit within their time and give us a focus of where we should expend our effort trying to make those times. Okay, so we might not be able to take 50 milliseconds off there. It's a what if tool. So I'm going to close that down. I'm just going to reset all these back. There we go. So we've set it back. Okay, so we've done these graphs here. We've done these. So these are my main analysis functions after an event has run. I can also filter, so I can say only show me the UI classes up here, or I can say it'll show me all. Okay, and we've got others, and you can do a filter that actually allows you to type in, and if I just hit capital P, it'll only show me things starting in capital P. There they are. So you can put anything there, but it basically puts a star on the end and finds everything that starts with that. Okay, we've got a few more things in here. So we've got save snapshots. We can actually save this stuff into a database. So if I click on save snapshot, it'll come up with a dialog. And in there I just need to name my snapshot. So I'm going to call it model plus data. There you go. So it's saving the snapshot. And when it's finished, it will say save snapshot complete. All that data, all of these samples effectively saved into the database. It's a little embedded database, but you can load it up separately. If you look at the manual that I've written, you can see where I actually connected up to OpenOffice, and you can do graphs in OpenOffice or whatever. So I've saved it. I can actually reset my timing. So if I'm in the middle of a run and I want to say, we make a little tweak and I want to capture the times from that point on, I can reset all the timings. The model is still there. Or I can actually say, right, I'm going to clear all my services, and therefore everything's gone. It's almost like it's been reset. Now I've cleared it all, let's have a look at load snapshot. So load snapshot opens up a little dialog and shows you all the snapshots you've got using the names you've given them. So I click on one and I'll say load snapshot. And there you go, it's loaded all the samples. It says loaded snapshot complete. So the time it's showing you is the time the snapshot was taken. That's actually what gets stored in the database. So your name is stored, but that's not the key. The key is effectively the long that represents the date time as GMT. And again, we've got them, so if you click on them, you can. It's loaded all the dependencies. It's loaded all of the data. So everything basically gets saved. So we've just loaded the snapshot, we've just saved the snapshot, and then we can clear the services and we can reset the services. So I'm going to clear the services now, because we're going to actually start looking at the real-time menu. The real-time menu allows us to watch data as it's going, so you can watch tests while they're running. I've actually got some data being generated. It's actually in a file in here called test.csv. There we go. And here we go, we've got some data coming in. So let's actually watch these so we can do a real-time graph. Let's just stretch that out, and we can open up as many of these as we like. I quite often have a screen full when we're doing tests, watching them go. It's useful to watch things because sometimes you get everything suddenly gets slow at the same time and then speeds up at the same time. And when that happens, you know there's something going on that's actually throttling everything else, and it gives you an idea of what to go and look at. So here we go, we've got these things running along. Four lines on this graph. The red line is your current time, so the last sample that came in, that's how long it took. The yellow line is the wait time effectively, so this point here waited for 100 milliseconds before it used. There we go, we've just suddenly shot right up. Yep, a couple of bad samples. You would expect that, it's a log normal distribution. This will tick along now. It only shows 1 minute worth of data, and then it's lost. Okay, now we know that process 1 actually calls process 2 op1, so this is dependent on this. And as you can see, when this shot up, the wait time on this shot up, and this went worse as well. So as you can see, things got a lot worse. You can actually have a perfect storm when both shoot up, and this certainly can go way up. And if you've got lots of dependent things, they can all join up, and you actually get a really bad spike. That's natural multi-tier system, unfortunately. So these are ticking along nicely. We've got samples coming in, and at any point in time, while it's running, we can actually have a look at my service frequency graph. Okay, we cleared all the previous data. So this is the data just that we've captured. And we can see the graph looks a bit funny, but that's because of the quantization, because we've not got many samples. This is a bit jagged, again because we haven't got many samples. But again, if I actually change my sample width, you can start seeing the structure appear. Yep. And it seems to be, because we've got very few samples, you need big buckets to actually collect enough things together to start seeing your structure. You can't really pick out the mode at this point, but we can actually see the structure appearing. One thing to note on that graph is there are no dependencies. When I'm capturing this data from these BW stats files, there's no dependency information. When I do it from our portal form, there is dependency information. It actually links it all up if the dependencies are not there, and it does all that in real time. So we've still got these ticking along nicely. So what I'm actually going to do is I'm going to simulate now some bad performance, suddenly some overhead in the system that's actually going to make this worse. So I've got a little command line here. It calls my test generator. The only difference from this and the line that was run here that's generating the data is this goes from a mean of 100 and 100 here to 400 and 500. So I'm just going to add that data in. Okay, so if we now watch this, we'll see the green line which is the running average, and we'll start to pull away from the blue. The running average is calculated over the last 100 samples. So because we've got these higher times coming in, potentially higher times, our green line and our blue line will start to diverge. Because the green line, of course, is 100 samples, they'll diverge faster, and then the blue line will slowly get pulled up. Whether you can see the blue line get pulled up, that's a different matter because of the scale of the graph. But you can see the green is slowly beginning to pull away. Get higher, and that will push it up here as well. And it'll also actually cause bigger spikes, and we'll see the time suddenly get worse. So the running average is very useful in that it actually allows us to spot this data, spot when things are happening. If things suddenly take a nosedive, or actually they even improve, why have they improved? What's suddenly driven them to go down? Some of our users stopped. As the system suddenly improved, as something actually stopped, that's actually improved the rest of the system. There we go, we suddenly had a little bit of a bad cluster there, caused by a little bit of a bad cluster here. But there we go, we've got a big spike here, not caused by a big spike here. So this process actually taking a long time. So it's useful to watch these real-time graphs, and they just run on and they'll run on and they'll run on. As I said, you can open up as many as you like. I'm going to close those down. We've actually got several other things. The load monitor file, if you've actually got lots of files you need to monitor, and it's always standard files, you can actually create a list of them instead of going one after another and selecting them all. You can create a list of the files, load it in with this, and it actually then links in all the files as though you clicked them all and said read that one and read that one and read that one and read that one. So it's just a shorthand. I found it tedious just to load them all up manually. The monitor tab actually tells you the files that are being monitored. So there you go, there's the one we selected. If I click on it, that would actually stop monitoring now. There you go, it's reading no more, and down here it says it's reached the end of the file, because we told it to reach the end of the file in this case. These are still running, still generating data, so I can actually link back up to it. It won't actually carry on from where it left off, it'll carry on from the end, so it basically starts tailing that log file from that point on. So let's stop it again. There's one other option in here, reset rate meters. So the rate meter here tells me the rate they were coming in. So we're coming in at 1.897 every second. Okay, we can reset that if we like. There we go, that just sets those back to 0. So it starts the rate meter count right from 0 again. Why do you want to do that? Sometimes if bits of a test have finished and you want to see what's going to happen afterwards, you can reset them and go, now what does it go to? And you can actually see it. But unfortunately it resets them all. So whether you do that or not is a different thing. Okay, there was another option on the front screen that we didn't actually look at, and that was the compare. What the compare does is it allows us to look at these numbers and actually compare them against a saved snapshot. So if I click compare, we've only got one saved snapshot, which was a model plus data. So I'm going to compare the numbers here against the numbers that were held in the model plus data. That actually opens up another little table for me. Fairly simple table in this case because there's only 2 entries. So it only shows those that match. So if I didn't have a process 1 op 1 in the snapshot, it wouldn't have shown me, and because I don't have any other elements that were in that snapshot we saved, we don't see them in the table. But what it shows me in here is process on op 1, the mean in the snapshot was 219, our mean here was only 803, so we're actually 265% worse, minus means worse, than the snapshot, the last save that we did. So we can compare test runs, so we've actually got worse. I know we've got worse because I created the data to be worse. I cheated really. So we're actually nearly 3 times worse than that, or whatever it comes out as. Yep, and we can do the same here. So we're 112% worse. Okay, so that allows me to compare different runs against each other, see if we're improving, how much we're improving. We can make a change, run another test, has it improved, and it gives us a record and it allows us to check. Okay, I'm just going to clear all my services now. I'm just going to stop that generating data. Don't want to fill my file system up. And there's one other function I'm going to look at, and that's load matches. What load matches does is it allows me to apply regular expressions to the service operation names, component names, function names if you want. And why would I want to do that? Well, not every system may generate and use the same name for the same thing. Okay, so if you think about it, what's being called at from the browser may be slightly different from what the portal sees it as, which may be slightly different from what the service thinks it's being called as. So you may have a mismatch. So this allows you to create regular expression matches which match these things and turns them all into the same name. Okay, so let's load up a match file. There is a match file on here I've created. It's called match.list. There we go. Match file's fairly simple. I'll just load that into this list. Here's my match file. Fairly simple. It's got a little string at the top that says this is a match. This is a match file. If that's not found, it won't actually load the match files. Then it says this applies to services. This can be either service or operation. So this only applies to the service part, and it says make sure it matches the whole service name matches process dot. So if it doesn't start process and then have one character afterwards, this line won't actually be called. And if it does, it says effectively change the dot, change process to P and keep whatever's in that dot. So if I load that up, I think I loaded it up already. Now whenever I create a service, whether it's from a snapshot or from a load file, it will actually apply that match, those match strings. There we go. So all those process 1 have all been applied. Okay, so that allows me to do regular expression matching. So we've actually looked at reset timings, clear, save, load, compare, loading files, loading matches, filters, the volumetric modeling, service frequency analysis part, the dependency matrix, the service times, and some real-time monitoring capability. As I said, this is all based on log file reading. So how does it work? How would you use it for your log files? The system is actually built to be extensible. You don't need to change this code. All you need to do is write a very simple extension. Okay, let me just close this down. And I'm going to open up my clips and show you one of those extensions. So here's my Eclipse. Just open up into my workspace. Okay, so here's some extensions. Standard extensions. Just wants me to log into my CVS repository. So standard extensions, I've actually written 4. So there's the model reader. We use the model reader to actually read. So we actually use an extension when it started. Model reader is quite complicated. You can have a look at this, but I don't actually intend to open it up. So let's have a look at the very simple comment reader. Guess what comment reader does? Well, it actually recognizes comment lines and then decides to do nothing with it. So here's my comment reader. It extends the real-time reader. Okay, that's important to extend the real-time reader. It needs that because that is what the load file part actually uses and the real-time monitoring actually uses. There's 2 methods you need to override, and that's all you need to do. One is get order number. You can prioritize your extensions so that one extension gets processed, your line gets processed through that extension before any other. It goes from the lowest number up to the highest number. So the comment line is number 10, and it checks any line that starts with a hash or a semicolon and says that's a comment line. So if you have a line that actually starts with a hash or a semicolon, you want it processed before this, you need to have an order number less than 10. Okay, it's undefined. If you have another one based on 10, it's up to the class loader to decide which one it would run it through first. So if you want to go before the comment reader, make your order number less than 10. All it simply does is it creates a service entry and repasses that service entry back if it matches, otherwise it returns null. The system, if it gets a null back, will then pass it into the next extension and the next extension until it's either exhausted all the extensions or it's had a service entry back. As soon as it's received a service entry back, it stops. Okay, and it says, okay, I found an extension that wants to process me, has processed me, nothing else will. Okay, there's a whole raft of information about the service entry format and the how to create a service in the documentation. Please have a read. It's very simple. So that's a most simple comment reader. We'll have a quick look at the model reader. As I said, the model reader is really complicated. Not really, just lots of different options. Exactly the same. It extends the real-time reader. It overrides the process log file line. And here's all the code. So it deals with different types, different model elements. Everything is in there. And it has an order number of 1. Okay, so that is the model reader. And it's not too difficult to create them. This uses all the different types of service entries. So it's there, you can create it. There's a sample code of using them, creating the different types. It's quite easy to use. So how does actually the system use it? Well, what we actually hook into is the new capability of Java 1.6 to do dynamic class loading. So it actually uses the real-time reader. So here we go, the real-time reader extension is the class it's overloading. So it's an abstract class, has a real-time reader, it implements comparable. The comparable uses the get order number. You don't need to worry about that, that's already defined. It's abstract. Here's the abstract methods that you need to override, and that is it. That's all you need to do. It's an abstract class, you can't instantiate it directly, you have to create the extensions. The extensions go in your own jar, and what actually tells the don't want that one, that would create. What actually tells the Java machine to load it up as an extension to this is in the meta-inf you create a folder called services, and in there you create a file with the name of your class you're extending, which in our case is typical analysis real-time reader extension real-time reader. Okay, that file then has some data in it, and it actually has your full class path effectively of your extension. So we've got 3 in here: beacon reader, comment reader. So it's beacon reader, as we got there. Comment reader, model reader. There is an example log file reader here. As you can see, that's commented out, so that never gets loaded because it's commented out. Okay, that's a quick overview of the Service Analysis Performance tool. I hope you found that interesting. Thank you very much for listening.